Hello and welcome to MUNSCI. Today we will be going through topic 3.1, which relates to thermal concepts, thermal physics. Essentially, we'll be going through all the concepts required, all the theory required, and then going through some practice problems, which are multiple choice questions. However, before getting into this video, please keep in mind that we will not be covering moles, molar mass, and Avogadro's constant. And we will not be looking at any long answer questions at the end of this video, only some multiple choice questions. This is because due to the nature of topic 3.1 being heavily integrated with topic 3.2, basically all of the long answer questions combine 3.1, 3.2, and the concept of moles, which we can't really look at. So that'll be in the next 3.2 video. So the first thing we're going to talk about is actually the states of matter, so the molecular theory. This is relatively simple actually, but this is good for revision so that you just have this at the back of your mind when going through all the concepts. So first, we're going to start with solids. Usually have a very regular structure with repeating patterns. So if we were to have some flat surface and we had some solid, let's say a cube, it could be of any substance. For example, ice. Ice is a solid. It's a regular pattern and it's in a uniform shape. It doesn't really need to be uniform, but it's in a firm shape. What needs to be kept in mind is for solids, the particles here, or you can call them atoms, you can call them particles. They can vibrate, but they never translate. So vibrating, yes. Translate, no. They don't have any translational movement. So that means they can't move from one place to another. That's just not how solids work. They stay in place, but they can vibrate. The energies of all of this will be explored once we're done with looking at molecular theory. What should also be considered is that they have strong intermolecular forces or bonds. So this use of intermolecular, like how the nature of the intermolecular forces or bonds is very important because it's asked many times throughout topic 3 tests. So keep in mind intermolecular. That means between the particles. So if we have two particles, then we have some sort of bond between each other. Again, this is not chemistry. I'm not going super in depth, but they have some bonds and they're pretty strong, which is why there's no translational movement. So for liquids, we usually have some kind of container because they tend to flow. So a liquid would look something like this because it tends to adapt to the container and it tends to flow. So because we know that now, it's pretty clear that of course they can vibrate, but they can also translate. If you got rid of this container, for example, these guys would just have a velocity going this way because they want to, of course, conform to the force due to gravity or weight. So essentially they can translate, and that's because they have weak intermolecular forces or bonds. Recall the intermolecular. This is very important. Intermolecular, they keep mentioning that. But do keep in mind that there are weak intermolecular bonds, but there are still intermolecular bonds. So you still have bonds between them. It would be a weak bond. It's not as strong as this, but it's still there. That's why these don't fly away. They're still sort of connected to each other. If solids were ice, for example, this was simply water, then what would a gas be in terms of water, H2O? Well, that would be steam. And to actually contain any kind of gas, we would need some kind of container. So the molecules or the particles or the atoms look like this. They're quite dispersed. And as I mentioned before, their velocities or the direction in which they're traveling will vary. So this one could be going here, this one could be going here, because they don't have intermolecular forces. So you could say very weak, it's no intermolecular forces. Now, what's called an ideal gas, which we'll actually look at later, has a bunch of properties. That's what we actually used. It's sort of like how we take air resistance to be true, but generally to make an ideal situation where we can easily apply mathematics to solve problems, because in the real world, obviously, not everything's perfect, but an ideal or perfect gas has no intermolecular forces. But this will be looked at more in 3.2. And they can fly in all directions. So now we'll be looking at temperature, absolute temperature, and the energies that are actually in play. And this is interesting because temperatures and the energies are actually tied very closely together. So what exactly is temperature? What is it? When you have some kind of substance and you stick a thermometer into there, the thermometer gives you some kind of reading, and that reading is usually it could be in Celsius, it can be in Kelvin. Usually it's Celsius. It could be in Fahrenheit, but in the IB we actually don't look at Fahrenheit. You don't need to know about Fahrenheit. And if Fahrenheit ever comes up in a question, they will give you everything you need, so you don't need to worry about this. But Celsius and Kelvin are two very important concepts that will be in the IB. So what exactly does this reading mean? Okay, if it's at this temperature, it means it's hot or cold. That's what it's a measure of how hot and cold things are. Okay, but again, what does that really mean? Well, what it's a direct measure of the average kinetic energy of molecules. So we're basically looking at EK, but we're looking at the average, so EK bar. And in the formula booklet for 3.2, actually, we know that's equal to 3 over 2 Boltzmann constant times temperature. And so we can see that, of course, this is just a constant. So the average kinetic energy is proportional to the temperature. So that's why temperature is actually a measure of the average kinetic energy. Now this is 3.2, so we won't actually get into using this equation, but this is just a good way to understand, or if you forget, you can just look at the equation and see, oh, okay, well, this is the equation, so temperature must be proportional to the average kinetic energy of the molecules. So it's a measure of the average kinetic energy of molecules. And this makes sense because, for example, when you're boiling water, let's say you're boiling water, you have some container here, you have it filled up with water, and you're boiling it. What we can notice is it starts to let off some steam. It starts to evaporate. That's what it's called, which I'm sure you knew, but we're going to cover that as well. And so you notice, oh, well, as temperature increased, this became steam, which meant the velocity of the particles actually increased as well, because they were in a liquid. It's not that strong. You could even think of it as like an ice cube. You melted it with the increase of temperature, and now the temperature has increased and the velocity has also increased because the particles are no longer just vibrating, they're actually translating because they're moving around when they become a liquid. In the same way, when they become a gas, they're moving around even more freely. The particles have a much greater velocity because they're moving around much freely. So we also know that temperature must have some proportionality or some relationship with velocity. That we can see, because if temperature is proportional to the average kinetic energy of the molecules, we also know that kinetic energy is equal to 1/2 mv squared. And this is interesting because if we take mass to be fixed, if the mass of the object was actually fixed, 1/2 mv, that also becomes a constant. If that's a constant, we can say that the kinetic energy is proportional to velocity squared. And that is even more interesting because that means that temperature is proportional to velocity squared, because temperature is proportional to the average kinetic energy of molecules. So that's really interesting, and that just helps understand how temperature works, how it's a measure of the average kinetic energy of molecules. If in a question they ask what is temperature, then you must state a measure of the average kinetic energy of molecules. Okay, so we know what temperature is now. We know what temperature is a measure of. But why do we have Celsius? Why do we have Kelvin? Why do we use Celsius in our daily life, but then we have Kelvin here? Also, make sure not to add the degrees, the degree symbol to Kelvin. It's simply Kelvin. Well, Celsius is based on water. And this is really helpful for these IB questions that have changes in phases in water, so going from ice to water to steam, all of that. It's really nice to know using Celsius. So at 0 degrees Celsius, water freezes, and at 100 degrees Celsius, water boils. It's based on water, which is very helpful. That's why we use Celsius. But Kelvin relates to the absolute temperature. What that means is at 0 degrees Celsius, water freezes. But at 0 Kelvin, any substance in particular reaches absolute zero. Absolute zero. What is that concept? Well, basically, the velocity of the particles is zero. We can think of it in that way. Obviously, I'm oversimplifying a lot because you don't need to know all these topics in depth. So when velocity equals zero, that means that the particles have no movement, no translation, and they also have no vibration at all. It's just fixed in place. These particles are just fixed in place. There's no movement at all. That's what 0 Kelvin means. Whereas 0 degrees Celsius means water freezes. So at 0 degrees Celsius, if you have a block of ice, the particles in that, if we take a closer look, the particles are still vibrating in that, there's still some vibration. At 0 Kelvin, there's no vibration at all. It's just there. It's just there. It's no vibration, no translational motion, nothing. And that's the difference between these two. So don't ever confuse these. 0 degrees Celsius and 0 Kelvin are two completely different things. Okay, but then how do I convert between the two? What's nice between the two is if you have a thermometer and you have a scale, you would notice that the spacing between these two for both degrees Celsius and for Kelvin are the exact same. So that makes it really easy to convert because we don't have any factors. We don't have any scale factors to multiply, for example, by 2 or by 1.6 or something. We don't need to multiply by any of those. All we need to do is add or subtract. And what I think you will just need to have to memorize, this is not in your formula booklets, but it's easy to memorize, don't worry, is that 0 Kelvin is equal to negative 273 degrees Celsius. This is something that you simply must know off by heart. 0 Kelvin is equal to negative 273 degrees Kelvin. And this makes conversions actually quite easy. If we use this formula, let's say we want to convert 3 degrees Celsius to Kelvin. It's something Kelvin. How is that? Well, we can use the rule that I just mentioned. So we know 0 Kelvin is equal to negative 273 degrees Celsius. And if we want to go from 3 degrees Celsius to Kelvin, well, we'll need to make Celsius the subject. So what we can do is actually add 273 to both sides. The reason we're able to do that is because Kelvin and degrees Celsius, as I mentioned before, are of equal magnitudes. So that's why we don't have any scale factor. So doing this, we get 273 Kelvin is equal to 0 degrees Celsius. Now, if that's the case, we could just add 3 to both sides now. And if we do that, we get 3 degrees Celsius. I'll just move this to this side. 3 degrees Celsius is equal to 273 Kelvin plus 3. And so that would be 276 Kelvin. And that is our answer. 3 degrees Celsius is equal to 276 Kelvin. Now we could also do this the other way around, which I think actually would be easier. 0 Kelvin is equal to negative 273 degrees Celsius. And if we want to convert, say, 33 Kelvin into degrees Celsius, how would we do that? Well, we just add 33 to the Kelvin side to make it 33, and we look at what it's equivalent to. So 33 degrees Kelvin is equal to negative 273 plus 33 degrees Celsius. So we get 33 Kelvin is equal to negative 240 degrees Celsius. And again, that's our answer. So it's just as simple as that. All we need to remember is that negative 273 degrees Celsius is equal to 0 Kelvin, or absolute zero. And using just this one equation, we can derive everything else. We can convert anything from Celsius to Kelvin or Kelvin to Celsius, because we can write it in the opposite form, which is 273 Kelvin is equal to 0 degrees Celsius. So memorize either one of these, whichever makes sense, and you can figure out any of these values. Here we have another question, which is actually looking at the conversions between Kelvin and Celsius. So a lump of metal is initially at a temperature of 100 degrees Celsius. So we can say that the temperature initially is equal to 100 degrees Celsius. The metal is heated so that its temperature rises by theta degrees. So the rise in temperature, which is just the change in temperature, is equal to theta. It's measured on the Celsius scales, theta degrees Celsius. The rise in temperature as measured on the Kelvin scale is, so this is quite an interesting one. We know that the 0 degrees Kelvin, absolute zero, is equal to negative 273 degrees Celsius. But keep in mind, we're looking at delta T. We're looking at the change. And if you recall, the magnitudes of Kelvin and Celsius are the same. Both Kelvin and Celsius, degrees Celsius, are the same magnitude. That means if we did even subtract something, the magnitudes would remain the same. So it's just data. That's all it is. We can't, because it's delta, if there's a change in, there's a difference. If there were no difference, if we were looking at, for example, the final temperature, and it said final temperature in the Kelvin scale, then we would have to use this formula here, or then we would have to actually convert. So the answer to this is simply B. So now that we've sorted that out, we can actually look at the internal energies of the substances or of the molecules. So let's just take a look. What exactly internal energy is? So E internal, or that we can say is the total energy inside of a gas, for example, must be equal to the kinetic energy plus the potential energy. We already know what kinetic energy is. Kinetic energy, EK, is equal to 1/2 mv squared. This is from topic 2, by the way. I don't know if I mentioned that before. And we'll actually take a better look at this when we look at the phase change graph, which we'll actually look at in a bit, which looks something like this. This is actually a very important concept. I will look at that in a bit. But what about the, I wrote K twice, I apologize, the potential energy. Well, potential energy is usually a negative value. Why is that? Well, because we need to do some work to break the bonds between two particles. Say we have two particles or two atoms or two molecules here, and they have some bonds. Well, to break apart these bonds, we'd have to do some work. There must be some work done to actually break these bonds. We need to do some positive work. But that's why the potential energy is negative. Because if we do some positive work, then we can get the potential energy, the potential in this, to 0. When the potential energy is equal to 0, we know that the state of matter, in this case, will be that of a gas or just an ideal gas, because the potential energy is 0, which means there are no intermolecular forces. So this is basically what we understand. So if we were to write all of this down in one way, if we know that the internal energy is equal to the kinetic energy plus the potential energy, we know that the kinetic energy relates to the velocities, it relates to the temperatures. When these are changing, that's what this refers to. The potential energy relates to the intermolecular bonds or forces, and is usually negative, or it can go to 0. So that's how that works. That's potential energy, and that's what makes up internal energy. So there are two components in this that we need to know. Whenever a question is talking about internal energy, they mean kinetic or potential, and you must identify which one is which one you need to actually use, and we're going to do that in some practice problems later. Here's another example question that we can give a try. The Kelvin temperature of an object is a measure of total energy of the molecules of the object, total kinetic energy, maximum energy of the molecules of the object, and the average kinetic energy. So which one of these will it actually be? Well, we can look straight in our formula booklet. As we mentioned before, this is 3.2, but we've already discussed this in this 3.1 video. The average kinetic energy is equal to 3/2 times the Boltzmann constant times the temperature in Kelvin. So we can say T subscript K. And we know that the average kinetic energy, therefore, must be proportional to the Kelvin temperature, because if we recall, this is simply a constant. This can be found in your data booklet. So we know this. Well, that means that that we can eliminate A. Well, why can we eliminate A? Well, the total energy, E total, is equal to the kinetic energy plus the potential energy. But remember, temperature does not measure potential energy. Potential energy is related to the bonds. And the bonds, we use the latent heat. This is quantified using latent heat. So this is definitely a no-go, because change in temperature definitely cannot define the potential energy. But the kinetic energy, sure. So we can already eliminate A. The total kinetic energy of the molecules of the object. Now this seems promising, but we need to keep in mind we're looking at the average. We're looking at the average here through the formula booklet. So this can't be true. It can't be total. The maximum energy of the molecules. Well, the maximum energy, we would also be using the potential energy, wouldn't we? So that can't be the case. So the average kinetic energy of the molecules of the object, well, of course, that's what it measures. The temperature measures the average kinetic energy of the molecules of the object, and must be D. So D is the correct answer. Okay, now that we've sorted those concepts out, we can actually start looking at the formulas in the formula booklet for 3.1. And the first thing we're going to look at is specific heat capacity. Well, what does the specific mean? What does the heat mean? What does the capacity mean? And thermal capacity. What is thermal capacity? What is all of this? Let's try and make sense of this. So, if we have some substance, let's say it's in a cube form, we could say it's ice. It has some specific heat capacity. And the formula that's given in the formula booklet is Q is equal to M delta T, MC delta T. Delta T we already know. That's in Kelvin, or it's in Celsius. The reason why delta T can be in both Kelvin and Celsius is because, as we mentioned before, the magnitudes are the exact same in both Kelvin and Celsius. So if we're looking at a difference, we're looking at the difference in magnitude, so it's going to be the same. You subtract, it's going to give you the same. That's why this can be in both Kelvin and Celsius. What about the M? What about the M, the C, and the Q? Well, let's start with Q. Q actually refers to heat, and heat we can call heat energy. And what you need to understand is, if we, for example, had this ice and we had some Bunsen burner or some kind of heat source, literally some heat source, some heat would be provided to this. What that means is some energy would be provided, in turn raising the temperature of this, which would cause it to melt. But that's essentially what it means. Heat energy is just energy supplied to this ice. So that's what it means, energy supplied. M, we're obviously going to look at how to use this equation, some examples. The M is just the mass, and that's the mass of the ice in kilograms. So yeah, of course, this is measured in kilograms. Heat energy, as this is energy, it's measured in joules. Temperature, as I mentioned, in Kelvin or degrees Celsius. And then we have the C. The C is what specific heat capacity is. C is specific heat capacity. What it is essentially a constant depending on the substance you're looking at. So for example, right now we're looking at water. And water must have some constant to make this equation work, because obviously if you plugged in some values into an equation and it wasn't water, then the answers would be different. If you tried to solve for the difference in temperature required for the amount of heat energy or heat supplied to it, you would need a different constant to actually to get the actual value. If you heated up water and heated up iron, they both have quite different results. One would heat faster. One would have a different delta T, have a different difference in temperature depending on the amount of heat supplied. Comparing iron and water, because of course iron is a metal which is in a lattice structure, but essentially all substances have different specific heat capacities, denoted by C. And if we rearrange this equation, Q equals mc delta T, we get C is equal to Q over m delta T. And this actually helps us define what specific heat capacity, or C, actually is. Well, we know that Q is measured in joules, we know M is in kilograms, and delta T is either in Kelvin or Celsius. I'll say Kelvin for now. And so if you were actually asked to define what exactly specific heat capacity is? Well, it is the amount of heat energy required to raise 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius in temperature. That's what the definition of specific heat capacity is, and we were able to figure that out using the actual equation just by rearranging it. And of course, the units, if you look at this, would be joules per kilogram per Kelvin. So that's essentially how you're going to look at it, the units of specific heat capacity. Okay, but then we also have something called thermal capacity. So what does that mean? Well, what we need to know is thermal is essentially an equivalent term to heat. Thermal capacity is equal to heat capacity. But keep in mind, what we just defined is not just heat capacity, it's specific heat capacity. This is all specific heat capacity. So don't confuse heat capacity and specific heat capacity. They're two completely different things. But thermal capacity and heat capacity are the same things. What thermal capacity is basically MC in this case. We have Q equals MC delta T, and that's what thermal capacity is. Instead of just having the C, thermal capacity is MC. That's the same with heat capacity. Heat capacity is also just MC. And that we can denote that with a capital C instead of a small c. So capital C is equal to M small c. So if we wanted to just use that, Q is equal to C delta T, we would be using the thermal or the heat capacity to find out all of these answers. So that's basically all it is. It's just MC. That's what thermal capacity or heat capacity is. That's what you need to keep in mind. And of course, the units of heat capacity, which is C, if we rearrange this, we would get C is equal to Q over delta T. So the unit is joules per Kelvin. So that's the difference. We specific heat capacity, joules per kilogram per Kelvin, but this is just joules per Kelvin. Here we have a question regarding the specific heat capacity. So the specific heat capacity, C, of a solid block of mass M is determined by heating the block and measuring its temperature. The graph below shows the variation of the temperature T of the block with thermal energy Q transferred to the block. Okay, so we understand that T is on the y-axis, Q is on the x-axis. So the gradient of a line, well, a gradient of a line is just rise over run. So rise over run. And run refers to Q. Rise refers to T. So if we take this into account, rise over run, so if gradient is equal to rise over run, it'll be equal to rise, which we're looking at T in the y-axis, over run, which is Q. And it gives us answers in terms of C. We should use the specific heat capacity in this. So T over Q must be equal to T, the temperature, all over Q is equal to MC delta T. This is actually also delta T because it's rise over run, change in rise. Why? Well, because looking at this, using the formula, look like Q is equal to MC delta T. So we just plug that in. Now we can simplify this a little bit further. The T's cancel, and we're left with 1 over MC as your answer. And that is correct, 1 over MC, which is D. So that's what we'd put in for our answer. Now let's look at all these things that we've learned and combine them and take a look at what does it actually mean in the grand scheme of things. How can it be applied? Why do I even need to know all this specific heat capacity, latent heat, and how do I apply it in questions? Well, we need to understand one kind of graph. On the y-axis, if we have the temperature, that can be in degrees Celsius or Kelvin, and this is the time taken. We can see that when we heat up a substance, it doesn't actually go straight up or have some kind of exponential, or in this way, it doesn't increase like that. It's actually quite an interesting phenomenon. And what we're going to do is tie in the internal energies with this, how the EK plus EP ties in, why these two are needed, the specific heat capacity, latent heat, and all of that. So we're going to apply that. What we've seen is that if you apply some heat or some thermal energy or heat energy onto some substance, then way in which the temperature changes is quite interesting. And the heating curve actually looks like this. So what the heck even is this? Let's try understanding this. Let's take a look at water for this example to understand what this curve actually is. Say this is 0 degrees Celsius and this is 100 degrees Celsius. What we notice is below 0 degrees Celsius, obviously, all of this, the substance or the water hasn't reached its freezing point. So it's still frozen here when it's under 0 degrees Celsius. So let's say this is -5 degrees Celsius, for example. It's still ice. So at this point in time, water is actually in its ice or solid form. So we understand that there is actually some difference in temperature here. There is some difference in temperature. And you realize, okay, we can use the Q equals mc delta T formula here. That means that this ice has some specific heat capacity. It has some mass, which I guess it would be constant throughout the whole thing. We looked at a system that is thermally isolated. So that thermally isolated means that the system is closed and heat can't escape and heat can't enter. So we're just looking at what's going on inside the system. So we can use Q equals mc delta T, but what about here? What about here? Let me come back to that for a second. Well, what we see here is as temperature is changing, the internal energy is actually changing as well. There's an increase in internal energy because we're supplying some energy, which is increasing the temperature of this. So there's an increase in internal energy. If we recall, internal energy is equal to the kinetic energy plus the potential energy. But right now, all that's happening is the particles are vibrating more and more. So the kinetic energy is actually increasing right now. The potential energy is not increasing right now. So here there is a change in kinetic energy, not potential energy. So what I will do is highlight the kinetic energy with pink, and areas where the potential energy is changing in green. So right now, obviously, the kinetic energy is increasing here. So this is going to be pink. But why is only the kinetic energy changing? Why is there no potential energy change? Well, temperature, if there's a change in temperature, as we identified before, that's proportional to the average kinetic energy of molecules. And that's why the kinetic energy, only the kinetic energy is changing in this case. So whenever there's a change in temperature, there must be a change in kinetic energy. So what that means is that this area here as well, and this area here, must all be changes in the kinetic energy. But then what about these plateaus? Why are there plateaus here and here? Also, what this means is essentially this is very long. It takes a lot of time for this process. Here it's still solid actually. Here it's still ice, but here we understand that it's water. So what that means is in this area of the heating change curve, this is where the melting process starts because it starts melting. It reached the freezing point. Okay, well it's no longer going to be frozen. So from here to here, it's melting. And same thing for this. From here to here, we understand, okay, it's not melting, but it must be evaporating. Why? Well, because here it's still water, but at this point it becomes steam. So we notice something very interesting. Okay, well here it's evaporating, but there is no real phase change in these areas. So keep that in mind. If there's a change in temperature, that means there's a change in the kinetic energy, but that means that there must be a change in potential energy here. Now I've just made a quick simplified version of the phase change graph, but why exactly does the kinetic energy change here? But then not in these areas. We already identified that the temperature is not changing, right? So the EK can't be changing. But keep in mind that we're still adding a constant rate of energy. We're still inputting some certain amount Q while we're doing it. What I mean is we started off with ice at this point, but because we're adding some heat, we're adding some energy or supplying some work into the system, the ice gains energy and therefore it reaches its freezing point, starts to boil, and then reaches vaporization points where it starts to evaporate here and then becomes a gas at this point. So it's still increasing in terms of its energy. And if you remember, the total internal energy is equal to the kinetic energy plus the potential energy. And if the kinetic energy isn't changing at these plateaus here and here, then that means that the only thing that can be changing is the potential energy. And the potential energy refers to the bonds between the actual particles. So that actually makes sense, because we realize that if there's some melting going on, that means that the ice is actually turning into water. That means that the bonds, or the forces between the two particles, must be broken down, or must be weakened. And that means that there's a change in potential energy, because potential energy, as mentioned before, relates directly to the intermolecular bonds. So therefore, the bonds are actually being broken or being weakened during this time. So there is a change in potential energy, but not a change in kinetic energy. That's why the temperature is actually not changing in these points. And this is where the concept of latent heat comes into play. Latent heat. Latent literally means hidden. And the reason it's hidden is because there's still some change in the internal energy going on, despite the temperature not changing. So if you had the ice block, and it was going through its melting process, so there was some water actually coming out. It was melting, and you put a thermometer in there. It would give you a constant reading during this time. During this time, the temperature is constant in these plateaus. So that means that EK is also constant, because temperature is constant. And as we know from before, temperature is proportional to the average kinetic energy of the molecule. So that's why all of this is constant. So that means that the potential energy, because the bonds are being weakened, is changing. The potential energy is getting less negative. That means it's increasing, because potential energy, as we discussed before, is negative. It's tending towards zero. It's not reached zero yet, because that's around this point when it's an ideal gas. But it becomes less negative. The potential energy increases. So there's still an increase in energy in general when we're applying all of this. But then let's take a look at latent heat. The formula for latent heat is Q equals mL. This L is what the latent heat is. Latent heat, or latent heat capacity. It's similar to heat capacity. And L is equal to Q over M. So it's in joules per kilogram. Now, coming back to this graph, let me just make a simplified version of this graph. We understand that latent heat is in play here, and latent heat is in play here. There are two kinds of latent heat. We have the latent heat of fusion and the latent heat of vaporization. Latent heat of fusion is when the substance is during its melting process. And the latent heat of vaporization is when it's in its evaporating process. And this helps distinguish where in this process the substance is. So if you understand, it's going from a liquid to a gas, they must be looking at the latent heat of vaporization. And if it's latent heat fusion, well, they must be looking at solid to liquid. And that's basically how you can distinguish the two: latent heat of fusion and latent heat of vaporization. And here, what you need to use is the specific heat capacity here, here, and here. But the actual definitions of these are quite simple. So let's take a look at the definition of these. Latent heat of fusion is it's essentially the amount of heat energy required to change 1 kilogram of a substance from solid to liquid without a change in the temperature. And the same is true for the latent heat of vaporization. It's the exact same wording, except it's from liquid to gas. Here we have a question regarding the phase change graph, and it states that a substance is heated at a constant rate. So we know that it's going to be this graph. As we mentioned before, to have this graph, we need Q over T, which is equal to power, must be constant, which is why this graph is formed. Otherwise, you would get some weird graph. This is why this is straight, and that's why we can use rise over run in the previous question to figure this out. The sketch shows a variation with time t of the temperature theta. of the substance. So here they use theta as a temperature. In which region or regions of the graph must there be more than one phase of the substance present? Well, this is a change in temperature, and if there's a change in temperature, we're looking at a change in the kinetic energies. That means there is no change in the bonds, no change in the potential energies right now, as mentioned before. So that means that this must be just one phase of the substance. That means this could be a solid, this could be a liquid, but there's not more than one. From x to y, we can notice that at the start, this is either going to be a solid or liquid, and it ends up from a solid to a liquid or gas. So in this case, we can take it as a solid going to a liquid. Because it's going from a solid to a liquid, if we take this point, for example, it might be some maybe 40% 40% liquid and 60% solid. Now these are just numbers that I've made up, but essentially in this region there is going to be some distribution between solid and liquid, because here it becomes fully liquid, here it's solid. So in this process there's going to be some solid, some liquid. So from x to y, it's definitely not w to x, definitely not y to z, because there's a change in temperature. So that can't be it either. So wx and yz, that has wx in it, so that can't be it. This has wx in it, this has wx in it. xy only, that's the case. So xy is the correct answer. One more important concept that we need to look at before we actually get into some practice problems is how exactly these properties, such as specific heat capacity, is determined. How do you determine specific heat capacity? Experimentally, it's quite simple. Say we have some container filled with some liquid that we want to know the specific heat capacity for. What we'll need is a thermometer to measure the actual temperature, and we need some timing device, such as a stopwatch, to see the time it takes. And the last thing we need is some kind of heater, so that we can actually supply some heat energy, so that we can see a change. This does require some topic 5 knowledge, but this is extremely important. So taking a look at the actual circuit, we have some kind of battery. Of course, we have an amp meter, and we have a battery, and we have a voltmeter, so we can actually see the voltage. Using the formula that's in the formula, Q equals mc delta T, we're trying to figure out what exactly the heat capacity is. First, because we're using a stopwatch, we can actually look at the power. That, as we know, power, which is in watts, is equal to energy or work over time, which is the same as Q over T, because Q is in joules. And we're applying power at a constant rate. We're heating it up constantly. So if we know that Q over T is equal to P, then we know that if Q is equal to mc delta T, we just divide it by T. So P is equal to mc delta T over T. That's the time taken. We can figure that out with the stopwatch, sure. Let's continue to solve for C. Pt is equal to mc delta T, and C is equal to Pt over m delta T. Using this equation, actually, we can figure everything that we need, because if you recall, we had a voltmeter and we had an amp meter. So we don't really need to know the exact power. We can simply use the volt and amps. Again, volt measures the voltage. An amp meter measures the current, V and I. There is one equation from the formula book that we know P, power, is equal to voltage times current. So we can rewrite this as C is equal to voltage times current times time, all over m delta T. We would know the mass, we would be able to know the mass of whatever this liquid is using a scale, so we can figure the mass out. This delta T, we can figure out using the thermometer here. The The time we can figure out with the stopwatch, and the current we can figure out with the amp meter. The voltage we can figure out with the voltmeter. So essentially we can figure out the specific heat capacity using an experimental method. And it's actually not that difficult. And this is very important because it comes in a lot of questions. And what we'll do is actually we'll try out one of these questions first. Here's a multiple choice question that looks at exactly what we just discussed right now. The specific heat capacity of metal block M is determined by placing a heating coil in its center, as shown in the diagram above. The block is heated for some time t, and maximum temperature change recorded is delta theta. There is one thing I needed to mention, that in Q equals mc delta t, this delta t could also be taken as mc change in theta, delta theta. They're both the same thing. Theta can be used as t in the IB. They tend to use theta sometimes. In a lot of the mark schemes for past paper questions, you'll see that theta is actually used in place of t. But you can use t or theta, whatever suits you. I personally prefer to use t. And we can use the equation that we use, Q equals mc. Here I'll use delta theta because they're using the delta theta in this question. So we realize that we can use time. So let's divide by time, because we know there's going to be some power that the heater has, right? So Q over T is just equal to P, which is power. So P is equal to mc delta theta all over T. And rearranging for C, we get C is equal to P times T all over m delta theta. And P, using the topic 5 equation before, we have an amp meter. We have an amp meter right here. We have a voltmeter right here. And we know P is equal to VI, which is the voltage times the current. This amp meter measures the current, this measures the voltage. So we understand, we can derive, we know all of this. So therefore that's equal to, P is equal to VI. Substitute that in, we get VIT all over m delta, sorry, that's not a very good delta, delta theta is equal to C, which is the specific heat capacity. This is our answer. So obviously the answer is going to be A.